I'm going to title this video Test Practice because on the test I have, man, I had that drawing somewhere. I have 6 different figures or images that I use, and I ask you tons of questions about them. So I'm going to use similar pictures in this practice, and so you can see exactly what the bulk of the test is going to be on. Again, this is something that's so much easier to explain in person. I hope I've done at least a decent job, but this is crazy. So let's try. Last time the video ended kind of abruptly because I don't know, it was weird. All of a sudden I couldn't see myself. I didn't know if what I was writing on my iPad was working. So I just kind of stopped talking and shut it off. But now it's taking a little bit to connect to my Zoom owner. Anyway, so these examples, I'll do another one too. And if you want to Zoom, do a personal Zoom meeting where we can have a dialogue about this, we could do that as well. Your test is going to be on Tuesday. This is taking forever. It's going to be on Tuesday for second and fourth period, the 19th. 10 o'clock for second period, 12 o'clock for fourth period. I think Bianca is going to jump in on that one because she can't be there for 8th periods. And then Wednesday, the 20th, at 10 o'clock, 7th period is going to take it, and at noon, 8th period is going to take it. I have no idea why this is taking so long. It's as if people don't want me to do these videos. And I can't imagine why people wouldn't want me to do these videos because I'm rocking these videos. It's awesome. I'm going to stop the share and see if maybe I can get it to work by resharing. So pretty much, who knows when or what is going to work. All right, there it worked. So back to my beautiful drawings. My iPad is really kind of being slow. Everything's being slow. There we go. Oops, didn't mean to do that. Okay, so back to this, we call this thing a Bohr model. Bohr is the guy that it's kind of named after, because remember, he was the one that came up with the fact that the electrons aren't just flying around out here like Rutherford said they were. He did get them out of the pudding, and we thank him for that. But they're going to be located in things called energy levels according to how much energy they have. Please don't think that these are things around the atom in the electron cloud. This is just an area. Electrons with the lowest amount of energy in this atom are going to be in the first level. And if you remember from my video, the first level can hold 2 electrons and then it's full. You have to understand it's not that big because it's the one closest to the nucleus. And these things that are flying around in there are negatively charged. And there's 4 fundamental forces, and one of them is the electromagnetic force. And the electromagnetic force is what makes opposite charges attract. So plus and minus attract each other, and like charges repel. They don't want to be near each other, and so you can't get too many in a ring or a shell. It just doesn't work. Too much repulsion. The second shell energy level can hold 8. The third one can hold 18 if it needs to hold 18, and then it goes on out to 32, 50, and so on. We won't go much past third period on these. Anyway, so I'm going to ask you some questions. And I want you to pause the video. As I said before, I want you to pause the video and try to answer them yourself before you listen to my answers. So the first thing is, what is the, and let's go ahead and get used to some abbreviations here so that I don't have to write the whole thing out. According to this Bohr model, what this Bohr model represents, what would the atomic number be? Let's go ahead. Atomic number is just going to be AH. What would the mass number be? How many protons are there? How many neutrons are there? And what is the charge on this particular atom? So what this model does, it just represents an atom or an ion. Remember that if it doesn't have a charge, it's an atom. If it does have a charge, it's an ion. If it's a positive charge, we call it a cation. If it's a negative charge, we call it an anion. So for this particular one, answer those questions, pause the video, and now here are the answers. The atomic number is going to be the number of protons. The number of protons in the Bohr models that I draw are always going to be the number following the plus sign. Plus represents proton because protons are positively charged. So the atomic number here is 14. I don't know why that's not working. The mass number, if you go back to the definition of mass number is a number of protons and neutrons. And so if we add those up, it adds up to 29. Remember, the mass number is not something you can find on the periodic table. It has to be told to you. I'm not talking about that decimal number. That decimal number is an average of all the isotopes. I'm telling you that we're talking about this isotope, this one, the one that has 15 neutrons. Number of protons is the same as the atomic number, so it's going to be 14. The number of neutrons is going to be 15 because I told you that later on with another representation. I'll show you how you can figure that out if we don't have a Bohr model. And then the charge, remember when we deal with charge, what two subatomic particles do we worry about? We worry about the one that has a positive charge, so we worry about protons, and we worry about the other thing with a charge, which is electrons. So how many electrons do we have? We have 2, let me chart with this. We have 2, 4, 6, 8, 10, 12, 13, 14. We have 14 electrons and 14 protons. That means that this is neutral. You can write neutral, or I would take just putting 0. Now, how do we identify who this atom is? This is an atom of what element? You go to your periodic table. You're going to go up to where the main group nonmetals are. There's only 5 of them. And wait, no, you're not. You're going to go to the metalloids. It's right by the main group nonmetals. You're going to find out that the element that has an atomic number 14 is silicon. So this is an atom of silicon. More specifically, it's an isotope of silicon. And another way we could write this is we could say that it is silicon-29. That's one way to tell me specifically what isotope. Or remember, the other way is silicon, and then you put the mass number in the upper left-hand corner. All right, let's try another one. Let's try, this thing is just being really stupid. If this doesn't pop up here, Miss Kelly's gonna be mad. She's gonna be real mad. Let's talk about that guy. All right, showed up. So let me ask you some more questions. Pause the video. First of all, oops. First of all, what element is this? Tell me who it is. Identify it by symbol or by the name. tell me the mass number. I'm not going to always ask you the same question on all of them. Give me the atomic number. And give me the number. I don't know why I started with that in. Give me the number of electrons and give me the charge. Pause the video. See if you can figure it out. And here are the answers. The element, by looking at its number of protons, which is also its atomic number, so I can go ahead and fill that in there. When we find that on the periodic table, you're going to find out it's a halogen called chlorine, as the symbol is Cl. Since I don't want to run into that blue dot, I went ahead and used the symbol. The mass number for this particular isotope is going to be what? Mass number by definition, number of protons and neutrons. What's 17 plus 17? 34. I have no idea what that music was. Number of electrons, let's count them. We've got 2, 4, 6, 8, 10, 12, 14, 16, 18. One of them's weird here. I made one of them blue. We have 18 electrons, which means its charge, it has an extra what? It has one extra electron. It's negative 11. Remember in the past, I would stretch the protons out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That's all 17 of chlorine's protons stretched out so we can see them. And then next to each proton, I would put one of the electrons. So we have 18 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, but there's 18. Let me change that for 1 second, and let me go to that. Let me make them the same color as the one I put up there. Okay, so this means since there's one electron that is not being canceled out by a proton, remember, it's just like math. +1 minus 1 is 0. So we have a neutral charge when a positive and a positive proton and an electron cancel each other out. It's neutral. But when we look at the whole picture, only 17 of them are canceled out. We have one extra electron, so that gives it a charge of -1. Why does it have an extra electron? Do you remember what I told you stable meant in the world of atoms? They want the outer shell, a little thing we call the valence shell, to have 8 electrons. And as a neutral atom, each one of these red ones represents what it was when it was neutral. The outside shell, 2, 4, 6, only had 7. It was 1 short. So what chlorine does, what all halogens do, is it finds somebody that's not holding on real close to one of its electrons, probably a metal, and he's going to steal it. And when he steals it, he gets this outer shell that's full. He thinks he's happy, and world goes on much like he's happy. All right, so let's do one more of these. Let's do one more if I can get it to pull up. So many awesome drawings in here. Well, they're not showing up. Oh, this guy is. Let's do that guy. All right, here's your questions. Who is it? Identify the element. Charge. mass number. Just those 3 questions. Pause the video, use your periodic table. You're going to find this guy on the left-hand side in the alkali metals family. And here are your answers. The element, this is sodium. It's not an S for the symbol because it's probably a Latin thing. I just remember that you asked, do you want salt on that? And you go, nah. But anyway, charge, let's do the mass number. It's easier. The mass number is going to be 11 protons that make it sodium plus the 12 neutrons that this isotope happens to have, and that's going to be 23. 23 is awfully close to the decimal number on the periodic table. The decimal number on the periodic table is like 23 point. I can't even see it anymore. I can't. I need glasses. I can't read my periodic table. It's desperate times if I can't read my periodic table. Anyway, remember that decimal number is the average of all the isotopes that we find in nature. Sometimes we can assume that if we round the average, that maybe that's the isotope that's found in the greatest abundance. And oftentimes that is true. It's not always the case. It's not the case with copper. Copper's number rounds to 65, but copper doesn't even have an isotope, copper 65. It has 63. No, it rounds to 64. What am I even talking about? Copper rounds. Anyway, forget what I said. I can't see it. Copper rounds to 64. And copper only has 63 and 65 isotopes. So we can't assume that its most abundant isotope is the decimal number rounded in that case, but lots of cases we can. Let's just pretend that never happened because it might have confused you. Anyway, and now let's look at the charge. So this little sodium has 11 protons. It's going to be easy to stretch out just 11 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, in this case, my electrons, I made them red, so let's keep them red. And let's go ahead and stretch them out. So we've got 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. As this ion is represented, it has 11 protons, which makes it sodium, but it only has 10 electrons, which means it has 1 proton extra, so it has a +1 charge. We, of course, would call this a cation. And what happened was, remember that I taught you that the second level can only hold 8 electrons. So it was full with 8, but to make it neutral, he had to have this other ring, and he stuck an electron in there. But by doing that, he made his outer shell, the valence shell, the one that wants to have 8 valence electrons, it only has 1. So he just made himself a long way from having a full valence shell. So if he takes this electron and gives it away, then this shell no longer exists. Remember, I said it's just an area, it's not a thing. And if there's nothing in it, it's not there, right? So that means the shell underneath it becomes its valence shell, and it's full and it's happy. Now, I said if he takes that electron and gives it away, well, who's he going to give it to? Well, how about one of the halogens that have 7 valence electrons and want just 1 more? And so when a metal such as sodium gives its electron to a halogen, they become a cation. The metal's a cation. The halogen is an anion. What did I say about opposite charges? They attract. That's called an ionic bond. So if sodium gives his extra electron to chlorine, they stick together because of the electromagnetic force of opposite charges attracting, and we have NaCl, table salt. That's kind of weird. Let's stop for now. I'm tired. I need to go take my dogs for a walk. And we'll do some more of this. But if you guys can do these types of interpretations, if I give you a Bohr model, can you tell me the atomic number? Can you tell me the mass number? Can you tell me the number of neutrons? Can you tell me the charge? Can you identify the element? If you can do all of that, you are going to be in good shape for a large portion of this test. There's another portion coming from other types of representation that we'll do in the next video. See you guys on the other side.